So now that we're able to draw molecules, we're going to start looking at our various functional groups. And the first in line are a series of hydrocarbons that are basically just carbon and hydrogen and arranged a little bit in a pretty straightforward way. So a lot of what we have to do is called a nomenclature or naming. So all of the rules that we have are going to come and we're going to apply the rules from the IUPAC, which basically have created a series of names that allow everyone throughout the world to talk about molecules in the same way. And we call this chemical nomenclature. So the rules are very, very systematic, and although the names aren't usually very clean and simple, they do show us exactly what is going on in a structure in a relatively accurate and specific way. So the reason for this is that without IUPAC names, we end up using common names. So a really simple example of a common name is formic acid. Now, formic acid, most people would know what it is, especially if you've been exposed to chemistry. Formic acid is based on insect venom, but using the IUPAC rules, so we always are treating the same thing, the molecules in the same way, this would actually be called methanoic acid. There's nothing wrong with common names as long as the people you are communicating with understand what those common names refer to. Similarly, acetic acid or vinegar would be called ethanoic acid through IUPAC names. So it takes us through this main branch of organic molecules, which are broken up into various things. So where we are going to go is we're going to start with hydrocarbons. And hydrocarbons form really two types. Things that are based on benzene, which we're going to call aromatic hydrocarbons. And then the ones that aren't based on benzene rings are going to be called aliphatic hydrocarbons. And the three that we're going to start with are alkanes, alkenes, and alkynes. And if we can learn to name those three types of functional groups or those three families of molecules properly, all the other groups sort of follow along with it. So we'll start with alkanes. Alkanes are hydrocarbon molecules that contain only single covalent bonds. They are absolutely the simplest ones we can possibly do because it is just carbon and hydrogen and there's no double bonds to really talk about. The simplest one would be one carbon and four hydrogens bonded. So this molecule here, methane. You can't have less carbon than that, so that would be the simplest alkane molecule possible. Because there are no double bonds and carbon has the maximum number of atoms bonded to it, which is 4, we say that this is a saturated hydrocarbon. So you probably have heard as you go to the grocery store or read recipes or follow nutrition, the difference between saturated and unsaturated fat. Well, saturated fats would be fats that have basically alkane chains, all single bonds attached to them. And unsaturated fats would be ones with double or triple bonds, or alkenes or alkynes in them, generally the alkenes. So with our alkanes, the molecules are going to differ from each other just by this group being added, CH2. And it sort of acts as a spacer as it makes the chain longer. A series of molecules like this, in which each member increases by the same structural unit, is called a homologous series. So that's what we're about right now, is we're going to look at a few different aspects of what this means. The second thing with alkanes is they have a generic formula. And it might be hard to see on here, but it is CnH2n plus 2. So if we know what N is, which is the number of carbons, we can always figure out what the formula should be. And that is just the molecular formula, not the structural formula. So in a situation where we have an N equals 5 or a 5 carbon chain, if we put a 5 in for N, then we do our math, 2 times 5 plus 2. So the formula for a 5 carbon alkane would be C5H12. We can extend this to a lot of different scenarios, remembering the generic formula for an alkane be CnH2n plus 2. So decane has 10 carbons, so C10, H, do the math, 2 times 10 is 20, plus 2, H22. A 9 carbon alkane, 9 times 2 is 18, plus 2 is 20. Undecane, 11. 2 times 11 is 22, is 24. So alkanes have a very predictable pattern, is all we are saying. This does not tell us what the name of the molecule is, because there are many, many, many different structures that have this molecular formula that would be chemically distinct, have different boiling points, and everything. So the big part of what we're looking at today is trying to get them named, trying to work ourselves through naming. So as the plan here is just to really get familiar with the systematic way we name things. So everything we do should be relatively logical. There's going to be a set of rules that you just have to follow. And if you follow the rules, you will be successful in doing this. So the biggest key to naming alkanes is to find the longest continuous carbon chain and give it a name. So for example, in a molecule where the longest continuous chain would be 5 carbons that I could find, put my pen down and go through and find it, I would have a pentane. So these are called the roots, the little beginnings to this word. And these are just the lower hydrocarbons, or up to 10. And it does continue up through all the way up past 20. There are names that continue on beyond this. But these are the most common ones that you're going to come in contact with. So we do call this the root. The root doesn't change for really any of the molecules that we're dealing with. It really just refers to the number of carbon molecules present. This chart here is something you should either commit to memory or have readily available until you do, because it is going to be really, really important as we continue to go through. So these are the roots of the molecules, which are based on the number of carbons. Where this gets complicated is not all alkanes are just one long chain of carbon molecules. They can be branched. So the name of straight chains are just from that naming chart we just saw. So for example, a 4 carbon chain would be butane, because that once again would be 4 carbons butane. And these are just the expanded moleculars that are completely straight chain. And when I say straight chain, I mean like this, no groups coming off. There are so many different ways that we can draw a molecule with, for example, C6H14. These all have that molecular formula, but they are all chemically distinct. So when we have these different ways of drawing the same molecular formula, we call it a structural isomer. There's no easy way to predict the number that you will get from a given molecular formula. A lot of times it comes down to just trial and error or experience. Let's do a little activity that we're going to try together here. So it says, what is the chemical formula for butane? Well, I pull out my reference chart because I haven't memorized it yet. Butane has 4 carbons. So 4 carbons, H, 2 times 4 plus 2, C4H10. So it says, what is the condensed structural diagram for straight chain butane? So CH3, that's 1 carbon, 2, 3, 4. Make sure every carbon has 4 bonds. Fill it in with hydrogens and make sure that that is the right number. So I should have 4 carbons, which I do, and I should have 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It says write out the condensed structural diagram for the other isomer of butane. So 1, 2, 3. Now I'm basically going to try and rearrange this molecule. So I have this still 4 carbons and 10 hydrogens, but it will be structurally different. So what I'm going to do is I'm going to draw out the 4 carbons like this. If I were to put the bond on the end, I would end up exactly with this, like this. It does say condensed, and it did say condensed above, but I've drawn out the complete. So H3C, CH2, CH2, CH3. So I have these carbons hooked up differently. It's still 4 carbons. So now we just count and make sure we have 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 3, 3, 3. 1 is 10. So this would be the other isomer. There isn't another one that would be distinct from that. Again, it comes down to trial and error. You have to look and make sure that you understand that it's not always obvious, or it's not always going to be clear. One of the things that this is one of those things that's wrong that we would see frequently on a test would be someone doing this. And draw it out like this, and they go, okay, well, that's different. But because Lewis structures or structural diagrams don't show us shape, this is exactly equivalent to that. So that would not be a different isomer than the one above. It is exactly the same, would actually generate the exact same name when we learn the name here. So it brings us to the main part of today, which is naming, beginning to name. So an organic name is made up of a prefix, a root, and a suffix. So the root is the number of carbon chains, the longest chain, and that's on this chart. So the root is based on the bold or the highlighted parts on this. So we just need to find the longest chain, and that will give us that. The suffix is what family of molecules or what functional group is present. The only thing we have learned so far is alkanes, so that's the only one that we will have on here. And where we have the prefix is going to describe any branches or any side carbon chains that are coming off the main. So the system is really, really straightforward. The biggest thing that we have to do is we have to make sure we get the longest chain. The thing that we're going to make a little bit different right now is this idea of alkyl groups. And this table of alkyl groups, and it's usually these ones that are the most relevant, these alkyl groups are chains of molecules that could be attached to the main chain, the long chain, and they just get attached at these little points here. So again, the naming here is relatively systematic, but just remember you have this table, and this is another little table that you either commit to memory or have easily available to you while you're trying to name. So we're going to go through a couple examples with the molecule, and I'm going to read through the examples, and then we're going to go to the bottom and we're going to apply it. So we're going to find the root. So to find the root, we find the longest continuous chain or ring in the hydrocarbons. The second thing you need to do is if there happens to be a case where there are 2 chains the same length, pick the chain that has the most side pieces or most branches on it. Step 2 is easy for you right now because all we're going to do is you find the suffix. So the only suffix we have right now is the alkane one, ANE. But there are a lot of different suffixes we'd add, and that will take a little bit of practice just recognizing what you have. Giving position numbers is about recognizing the branches, and then give a consecutive number to every carbon in the main chain. You must start at one end of the molecule and work your way to the other, and you always start numbering from the end of the molecule that gives the lowest numbers to all the branches. And that again is just something that we're going to have to practice and get used to. So the last thing we have to do, which is really, it's pretty straightforward, but at the same time there's a lot of little pieces to it. So we need to name each branch. That's what we do for the prefix. We give each branch a position number based on step 3. If more than one branch is present, write the names of the branches in alphabetical order. If there are 2 or more of the same type of branch, use a prefix, so like di, tri, tetra, etc., to tell you how many, and that would be a really big step to not miss. We use hyphens to separate the words from numbers, use commas to separate the numbers. And finally, place the numbers in ascending order. And then you put it all together. So this molecule here is sort of a hybrid between a line diagram and a condensed structural. So what we've done in the program that I use to do this is it puts in the terminal carbons. So this CH3 is the chain, so is the end of the chain. So we need to find the longest continuous chain. I usually do that with a highlighter. So I just go through and count 1, 2, 3, 4, 5, 6, 7. So you need to find the longest chain. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it doesn't really matter, but we're going to name those as our longest chain. So we have our longest chain. Now we need to do position numbers. So we have to start at this carbon or this carbon in number. And we have to number in the way the branches will get the smaller number. If I start from here, it'll be 1, 2, 3, 4 will be the first branch. If I start from this side, it'll be 1, 2. The first branch will get a 2. So we start numbering our carbons from the side that gives the branches the smaller number. So we number our carbons. The next thing we have to do is identify the branches. So that's where this chart comes in handy. So CH3, well, that is a methyl group. And whether it's written CH3 or H3C, doesn't matter. So that's methyl, that's methyl, and that would be, there's a carbon here and a carbon here. So that's 2 carbons. So that's ethyl. So almost there. So we have 7 carbons in a chain. 7 carbons in a chain would be, the root would be hept. So I have hept. Longest chain, just write out the root for it. It's all single bonds, so it's the only ending we have is ane. So we know it's going to be heptane. So now we need to do the prefix. We have a methyl group and we have an ethyl group. And the methyl group and the ethyl group are done, we're going to put them together, but realize we have 2 methyl groups, so we'll put out in front dimethyl. We have 1 ethyl group, so we're not going to do anything with it. The methyl groups come at position 2 and 3, so this one's hooked to 2, this one's hooked to 3, and the ethyl is hooked to 4. So then what we do is we start by putting it together. We have to put the prefix in order, and when you're doing your ordering, you put it together in alphabetical order based on the name of the alkyl group. So there is a D here, but that doesn't matter. We're going to alphabetize based on the M in methyl. So ethyl comes alphabetically first, so it's 4-ethyl, 2, 3, dimethyl, heptane. So now we're just going to take those rules and apply them to as many situations as we can. So we go through them the same every single time. 1, 2, 3, 4, 5. So find our longest chain. 1, 2, 3, 4, 5. I'm going to take the straight one. We number so the branches get the smallest number. 1, 2, 3, 4, 5. 2. It doesn't matter which way we go. They're both going to give the same numbering. So we number. We have a 5-carbon chain, so that's pent. Where I'm getting that information is from our branch chart. So I have 5 carbons. That's pent. It's all single bonds, so it's ANE. It's the only suffix we have right now. Now we have to name our groups. So this is a methyl. And again, remember you have this chart. So CH3s by themselves is called methyl. So I have methyl, methyl, and methyl. So I have 1, 2, 3. So that's tri methyl. I don't have any other types of groups, so I don't have to put them in order. And the last thing I have to do is put them in the numbers out in front. So position 2, 3, and 4. So 2, 3, 4, trimethyl pentane. We do the same one here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4. 2, 3, 4, 5, 6. I think I got the long one. So number, so your branches are going to get the smallest number. 1, 2, 3. 1, 2, 3. So 1, 2, 3, 4, 5, 6. Number. This is a methyl group. This is a methyl. You'll start to get really familiar with these. CH2, CH3 is ethyl. And I have a 6-carbon chain. So we got to write them in order. You can do it left to right, or you can put it all together. I know that a 6-carbon chain is called hexane. I know that I'm going to have dimethyl because I have 2 of them, and I know I'm going to have an ethyl group. I know the ethyl is at position 4. I know that the methyl groups are position 3 and 4. I know, and then ethyl has to come first because E comes before M. So we write 4 ethyl, 3, 4 dimethyl. Remember that di, and then hexane. So once again, it's really methodical. It's the same thing all of the time, and you just really have to pay attention to all the little rules. So what you should do now is you should pause the video and try these questions, and then if you get stuck or when you're done, just resume. So for A, we do the longest chain. We number so the branch is closest to the smallest number. So for A, I have a methyl group at 2, so I write 2-methyl. And a 4-carbon chain is called butane. So 2-methylbutane. For this one, write the longest chain. 1, 2, 3. Could have been the other way. It's exactly the same. I have 2 methyl groups, so I'll write dimethyl. I have them both at 2, so you have to write 2, 2. If you use the prefix di, then you have to have 2 numbers. The prefix and the number of numbers out in front have to equal. in a 3-carbon chain is called propane. So 2,2-dimethylpropane. For this one, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. 1, 2. I have a branch at 1, but if I start from this side, branches will get smaller numbers. Number your chains. I have a methyl here. I have a methyl here. And I have an ethyl here. So I have a dimethyl and an ethyl. And I have a 7-carbon chain, which would be 7 is hept. So heptane. So 3-ethyl. Ethyl always will go out in front of methyl. 2,5-dimethyl. And a 7-carbon chain is heptane. So we move down to D. 1, 2, 3, 4, 5, 6. It's got to be the longest one. 1, 2, 3, 4, 5, 6. I have 4 methyl groups. So that's going to be 2, 2, 4, 4, tetramethyl, tetra for 4, tetra in 4 numbers, and a 6-carbon chain is hexane. Check your chains. 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. So we're going to go this way. The more branches out there. So methyl, 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 we've done those ones. CH2, CH2, CH3. So 3-carbon chain is called propyl. So we number from this way because it's going to give the branches smaller numbers. 1, 2, 3, 4, 5, 6, 7. So propyl, this is propyl. P comes after M, so methyl is going to be first this time. So I have 2, 2, 4 trimethyl. Tri because there's 3 of them. 4 propyl. And 7 is heptane. So again, the numbering and the naming are just, it's going to be the same thing over and over and over again. The opposite version of this, which generally is thought to be easier, is drawing them. And usually we just draw them in condensed form, but some people just jump and do the line diagrams right away. So the rules for drawing them are basically a lot easier. So look at the name, identify your root and the suffix. So if I had 2,3-dimethylhexane, I would basically be looking at this to start my chain. Hex would be 6 carbons, so I would draw 6 carbons connected to each other end to end. Don't write your hydrogens in yet. Assign one end of your molecule to be number 1. And it doesn't really matter which one you do. So if I did 1, 2, 3, 4, 5, 6, and one of the ways this is easier is you're creating the chain and you're creating the numbering. So it's really hard to mess up your own numbering. Add your branches. So we have a methyl at 2 and a methyl at 3. So we put it on 2 and 3, as you can see. Finally, we go along and we would add the hydrogen. So I have 1 carbon bond here. I need 3 more bonds. I have 3, I need 1. I have 3, I need 1. I have 2, I need 2. You just fill in whatever's missing with your hydrogens. It gets a little bit tougher if it's an alkene because you have to find the double bond. But normally they'll tell you where the double bond is in the name. So by normally they always would have to. And then you're good to go. So we'll practice doing it. Realistically, again, we generally use this on a cheat sheet, but you need your roots and you need your alkyl groups right there. So with butane, that's 4 carbons, so CH, sorry, I should do it the same way, C, 4 carbons, fill it in, that's butane. 3-ethyl octane, so oct is 8 carbons, so 1, 2, 3, 4, 5, 6, 7, 8. There's an ethyl group at number 3, 1, 2, 3. Here's my ethyl group from my alkyl chain table. Fill in your hydrogens. And you're done. So the next thing you're going to do is you're going to add your carbon chain. So we have 7. 1, 2, 3, 4, 5, 6, 7. We have a methyl group at 2, an ethyl group at 4. Fill in your hydrogens. So you control the numbering, so as you can see, it's quite a bit easier. Pentane, 1, 2, 3, 4, 5. We have methyl groups. We have 2 of them on number 2. Fill it in. And you're done. Again, it's considerably more straightforward. So now just to sort of challenge ourselves, and I've seen some people that draw the condensed and then go into line diagrams. We'll try and go right for it. So identify your root, so octane. So 2, 3, 4, 5, 6, 7, 8. I have an ethyl group at 3. I'm going to write in my alkyl chains as condensed form. And I have a methyl group at 3, and I have a methyl group at 4. So 2, 3, 4, trimethylhexane, so hex is 6. 2, 3, 4, 5, 6. I have a methyl group at 3, 2, 3, and 4. That's it. Heptane, 7, so 2, 3, 4, 5, 6, 7. I have a methyl group at 3, another one at 3, 2, 3, 4, and an ethyl group. Then decane is 10, so 2, 3, 4, 5, 6, 7, 8, 9, 10. Not the best line diagram, but so 1, 2, 3, 4 ethyl. Again, we've done these ones a lot. 5 methyl, and 6 is isobutyl. So 1, 2, 3, 4, 5, 6. So we're here. So isobutyl, we will draw this one. And there's your isobutyl. Again, you can do these with line diagrams as well, but this is generally fine enough. So now that we have these done, just a little note, I guess, is if you do want to just do straight line diagrams, it looks very similar. You just have to be a little bit really careful with it. So heptane is 2, 3, 4, 5, 6, 7, and then 1, 2, 3. You can put your 2 methyl groups on like that, and your ethyl group, which is at 5, 1, 2, 3, 4, 5, would be 1 and then 2. So these two are equivalent structures. Just I find this one is more descriptive than this, but they are in fact, of course, the same.